the homework at the end of this. And you're going to find that there's one part that I have that I think you don't have. Or no, oh, I didn't change it on here. Okay. Well, there's something I want to add, or I might just do it tomorrow. It'll be fine. Okay, so we're going to look at something called sigma notation. If you took honors algebra 2, did you guys do sigma? Yeah, okay, good. And then those of us in algebra 2 regular, I don't think we did sigma. So let me explain what this is. Sigma notation is a condensed form of showing addition. And so later this year, we're going to look at sequences and series. And a series is where you add numbers together. Well, you can have an arithmetic series where there's a common difference, or you can have a geometric series where there's a common ratio that you're multiplying by. So the sigma notation looks like this. And I don't know, I write it like this. I know my math type software makes that little indent. I don't write it like that. But what it's saying is this is called your index, your indices. This says the letter I runs from 1 to n. So it goes 1, 2, 3, 4, 5, 6, and so on. It does not have to start at 1. It can start at 0. It can start at 4. It can start anywhere you want. But if I have the sum where I runs from 1 to n of x sub I, that's x sub 1, because I put the 1 in, plus, and I go to the next number, x sub 2 plus x sub 3, up to x sub n. So what's really interesting is we can look at that binomial theorem through the lens of sigma notation. So if I say to you, I want to do the sum where r runs from 0 to 4 of 4cr. So this is going to go 4c0 plus 4c1 plus 4c2 plus 4c3 plus 4c4. So sigma notation is helpful. It just condenses instead of us writing all of that out. Well, Pascal's triangle is credited to French mathematician Blaise Pascal in the 1600s, but the triangular array of numbers appeared in a Chinese document printed in 1303. The binomial theorem was known in Eastern cultures prior to its discovery in Europe. The same mathematics is often discovered or invented by independent researchers separated by time, place, and culture. So if you remember Friday when we started the notes, I said, hey, this was in Western and Eastern culture. And I said, well, you had to wait to find out. So they were really in hundreds of years. So this was a big jump in time that two separate people were working on it. So the binomial theorem can also be used to solve counting problems involving experiments with only 2 outcomes. So if I have a coin and it's flipped 5 times, how many of the possible outcomes have at least 2 heads? So what we can do, this is really cool. You can actually take a binomial, so there's only 2 outcomes on the coin. You can either get a head or a tail. So watch what this looks like with binomial theorem. This will be the 5 choose 0 heads. This means really that you have 5 heads. Then 5 choose 1, and it will be h to the 4th, t to the 1st. Then it's going to go 5 choose 2, h cubed t squared. 5 choose 3, h squared t cubed. Plus 5 choose 4, h t to the 4th. Plus 5 choose 5, t to the 5th. And do you remember that the n choose r is the same thing as the NCR? Okay, those are in fact equivalent notations. So our question here A coin is flipped 5 times. How many of the possible outcomes have at least 2 heads? Well, let me finish this. So this is 1 times h to the 5th. I know the second one will be a 5. Does anybody remember what would the 5 choose to be? You had to do it. That's 5 factorial over 2 factorial, 3 factorial. So it's 5 times 4 over 2, 10, right? Yeah, so it's 10. Now let's work smarter. If I go backwards, this is a 1t to the 5th. You know it has symmetry, right? There's symmetry in those coefficients. There's symmetry in Pascal's triangle. So this is a 5. So without even doing the work, this one has to be a 10 as well. So what this binomial represents, the h plus t to the 5th, this represents flipping a coin 5 times, and these are your outcomes. There's 1 way to get 5 heads. There's 5 ways to get 4 heads with 1 tail. Think about it. You could do tail, head, 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 head. You could do head, tail, head, head, head. You could just move that tail in the 5 different positions, okay? There's 10 ways to get 3 heads and 2 tails. That is a 3 there. There's 10 ways to get 2 heads and 3 tails. There's 5 ways to do 1 head with 4 tails. It's the same as this one. And then there's 1 way to get 5 tails. So let's go back to the question. And you got to be careful because it's saying at least 2 heads. So look at these options. Look at these options and how many so if I want at least 2 heads, how many are there? I just heard it whispered. So 2 heads, doesn't that start here and go to the left? Yeah.
These 2 heads would have 26.
Yeah, 26. You're going to do 1 plus 5 plus 10 plus 10. So there are 26 possible outcomes. Okay, the 1 plus 5 plus 10 plus 10. Because the last 2, there are not 2 heads. So, binomial theorem is used in counting problems. You can also do it to do some probabilities, which is neat. All right, so far what's new is the sigma notation and then looking at counting problems. Now we're just going to go back to what we know. It says, recall a binomial is an expression consisting of 2 terms, such as a plus b. If you want to expand a plus b to the 7th, there's 2 ways to get the coefficients. You can go all the way down to the 7th row of Pascal's triangle. That can be a little bit tedious. The second way, and if you have a graphing calculator, there's actually a way to very quickly get all of your NCRs. So if you have your graphing calculators, let's try this together. You can use your calculator, so you can do this on a scratch pad or the graphs page and look at a table. It says you can enter, so let me see. I'm going to try it on a graph and see. So it says you can do, and if you press menu, enter.
Scratch pad, you can just type NCR in 2 parentheses and
Oh, okay, on a scratch pad. So you did your So, okay, on a scratch pad, so you did number 5, right? Probability. Number 3, combinations, NCR. And did you do 7, X? Because it's saying I could put it and then it would do all 7 for me. See, that's not working, but I'm
Do
not.
it on the graph and then open the table. That's
Okay, so when you're on a graph, that's what I was trying, but I couldn't. When you add a graph, so can you tell me, how did you get the NCR?
You can literally just type in NCR.
Oh, NCR, okay, N.
N.
Did you have to make a capital C?
I did. But I don't know if that makes it.
You don't need to make it a capital.
You don't, okay. NCR, then did you do a parenthesis 7, X? Okay. And then how do you add your table? Control. Oh my gosh, isn't that cool? Okay, help each other, okay? So you literally open a graph, okay? Open the graph and just type, and I didn't have to do the capital C. I did NCR, let me write it here. I did NCR, parentheses 7, X, then you hit Control T. And it literally gives you those coefficients right there. 1, well, it starts at 0, right? So, oh my gosh. So there's your 1, 7, 21, help each other, 35, 35, and then it should be symmetric, 21, 7, 1. So there's your coefficients. Isn't that cool? That is super cool. All right, so with the expansion, write a plus b to the 7th with the aid of your calculator. So now we've got all those coefficients. You're right, so big. Notice that the sum of my exponents is always 7. There we go. So I can tidy this up. I probably could have done it in one shot. Turn to your neighbor and ask, like if you're stuck, you're like, how are you doing this?
How are you doing?
Yeah.
What's the deal?
I just got Oh, okay. So, here we go.
How do you do the
So we're gonna do a new graph. Add. Let's do it. I'm gonna do save that.
Control T?
Okay, so you have to do the NCR parenthesis 7, X here. Okay, press enter. Then do your Control T. I think you tried to do the Control T and put it in there. Yeah. All right. Okay, so what I want you to do is example 1 and example 2. Try these. I'm going to give you a little bit of a head start on me. If you'd like to use the calculator to get those coefficients quickly, you can do that on these. Be careful with the minus sign. Okay, be careful with the minus sign. Then when we're done with example 1 and 2, I'm going to stop and you're going to move into your usual groups and you're going to do the in-class work. If you happen to finish all that, the very last page, I kind of scrunched the homework. So you're going to use separate paper for the homework. And then I have an answer key, but you need to show work. Okay, you need to show work. So let me give you a little bit of a head start on me. Okay, so yeah, all right. Let's.
It's also about to die.
Okay, all right. So So here's what you're going to do. You're going to add a graph,
Okay.
and then you're going to type here, NCR parentheses.
How do you know what to put in the parentheses?
Okay,
Like for
because
the-
it's the seventh exponent, it's
Okay.
7 comma x. Then it gives me 7, 6, 5, 4, 3, 2,
So
1.
here you would do 5.
Yes, you're going to do 5 comma x, close it, and you're going to press enter. Now you do your control T.
Okay.
And there they are. You do have to start at 0, because if you remember the NCR, it goes n over 0.
Choose here.
Yeah. So it does start there.
Thank you.
Mm-hmm, sure. And what I'm hoping is that once you do enough of these, like a third power is 1, 3, 3, 1. You know, your fourth power is going to go 1, 4, 6, 4, 1. The 5 is 1, 5, 10, 10, 5, 1. Like, you should begin to just remember them because you're doing them so often. So I'm going to set up number 1. This is kind of what I would expect to see. So you're going to stick the negative with that 3. And it makes a difference. So you're getting those coefficients. So so we've done Pascal's triangle, we've done binomial theorem, and now we're getting the calculator to do the binomial theorem for us. Okay? All right, here's my answer for example 1. Here, as you press enter. And press enter. Now try Control T. There it is. Yeah, you have to press enter. Yeah, you do have to press enter. All right, now example 2. When you're ready, uh-oh, this one's going to get interesting, okay? Something I want to point out in example 2. That's not a negative y, the quantity squared. It's negative times y squared. Okay, it's a negative times the y squared. All right, when you get there, check this. I had 16x to the 4th minus 32x cubed y squared plus 24x squared y to the 4th minus xy to the 6th plus y to the 8th. So what I want you to notice, so I took it up a notch from what we did Friday, is my x's went x to the 4th, x cubed, x squared, x, and no x. But notice the y's. There was no y, y squared, y to the 4th, y to the 6th, y to the 8th. Why did the y's change that way? Why did the y's change that way? Anybody?
So there's an exponent within the parentheses.
Yeah, there's an exponent within the parentheses. Okay, push into your groups. And now I want you to do the classwork together, okay, where it says in class. Try to expand these, and then try to keep going till you hit the homework part.